At the far end of our sun's breadth, the map goes blank. Blank isn't empty. It's a boundary, our star colliding with the galaxy. Tonight, we go there with the only witnesses we've ever sent, Voyager 1 and 2. We'll hear space itself ring, and from that tone, read the true density of the interstellar medium. We'll watch magnetic fields drape around our heliosphere and steer cosmic rays like rails. We'll see how this invisible weather shields worlds, sculpts atmospheres, and sets the rules for travel between the stars. From the sun's bubble to the galaxy's tide, we'll sketch the first clear map of the edge and what waits beyond it. Stay with us. By the end, you'll know where home ends, what lies beyond, and how we get there next. Maps end. Curiosity doesn't. What if it is alive with hidden forces, a frontier humming with unseen energies? For millennia, humanity has looked to the heavens, charting the movements of planets and dreaming of distant stars. We built our maps of the cosmos based on what we could see through telescopes, a universe of light and shadow. We saw the sun, the planets, the asteroids, and the comets. We thought we understood our cosmic neighborhood. But past Neptune, the familiar map fades, and a hidden frontier begins. We thought we understood our cosmic neighborhood. But beyond the orbit of the last planet, Neptune, lies a realm that was, until very recently, completely invisible to us. Only recently have our machines slipped across that threshold. Not with blazing rockets, but with patience, decades of quiet travel into the dark. Out there, sunlight thins, heat fades, and the rules begin to change. The edge is not a line. It is a region, messy, shifting, alive. We didn't rush to it. We drifted there, on patience, math, and faith in two small machines. At the edge, the familiar rules loosen, and the galaxy begins to speak in a quieter voice. We're going to learn how to hear it. Space, we are often told, is a vacuum, an empty void. But that is not entirely true. While it is far emptier than anything we can create on Earth, space is not a perfect nothingness. Between the stars lies a tenuous, almost ethereal medium. It is an invisible ocean of gas, plasma, and dust. We call it the interstellar medium. It moves. It flows past our sun like a slow wind, carrying faint magnetism and relics of ancient stars. Sometimes it's warm and rarefied, sometimes cooler, denser, and threaded with magnetic strands. We live inside this ocean, whether we notice it or not. This medium is star stuff in transit, the material from which future stars, planets, and maybe life itself will form. Our sun is not just a source of light and heat. It is a powerful engine, constantly spewing a torrent of charged particles into space. This outflow is called the solar wind. It travels at incredible speeds, often exceeding 1,000,000 miles per hour. This wind rushes past all the planets, creating a vast, protective bubble that envelops the entire solar system. This bubble is known as the heliosphere. It is our home. Inside this bubble, we are shielded from the harsh realities of interstellar space. At its outer reaches, the solar wind slows from supersonic to subsonic speeds. It piles up, turns turbulent, and finally meets the pressure of the galaxy beyond. Think of weather fronts colliding. Only here, the air is plasma and the fronts are magnetic. First, the solar wind slows, like a river hitting a broad delta. Then it stirs a rough country of eddies and shocks. Finally, it meets the quiet push of the galaxy and yields. That last give is the boundary. And somewhere in that turbulent borderland, our shield ends and interstellar space begins. That is the line humanity has crossed. In the late summer of 1977, humanity launched two remarkable spacecraft. They were called Voyager 1 and Voyager 2. Their initial mission was to conduct a grand tour of the outer planets, Jupiter, Saturn, Uranus, and Neptune. This was a once-in-a-lifetime opportunity, made possible by a rare alignment of the planets. They skimmed cloud tops, threaded ring shadows, and watched moons pull at one another like clockwork. Each encounter bent their path and flung them farther from home, setting a course not just across the solar system, but beyond it. The grand tour was the beginning. The interstellar journey was the consequence. The Voyagers did not just visit these worlds, they transformed our understanding of them. At Jupiter, they discovered active volcanoes on the moon Io, a finding that stunned the scientific community. For a spacecraft to journey for decades through the cold, dark expanse of the outer solar system, it needs a power source that is both incredibly reliable and long-lasting. The solution they chose was a remarkable piece of nuclear technology, the radioisotope thermoelectric generator, or RTG. Each of Voyager's 3 RTGs contains pellets of a radioactive element, plutonium-238. The warmth of that decay feeds simple thermocouples. No pistons, no pumps, just heat becoming electricity. Year by year, the fire dims. So the craft make do. Fewer instruments at once, longer naps, careful choices. Deep space rewards patience. As the Voyager spacecraft travel farther from home and their power supply slowly wanes, not all of their original instruments can remain active. However, a select suite of instruments remain operational. One of the most crucial surviving instruments is the magnetometer. Mounted on a long boom to keep it away from the spacecraft's own magnetic interference, this device measures the direction and strength of the magnetic fields. Another instrument listens instead of looks, the plasma wave subsystem. It hears the quiet ring of electrons around the ship and turns that tone into a number. The cosmic ray detectors keep count of the high-energy hail. Small signals, big meaning. As the Voyager spacecraft soared toward the unknown, scientists on Earth waited. In August of 2012, Voyager 1 sent back the data everyone had been waiting for. The solar particle counts plummeted. The galactic cosmic ray counts shot up. The transition was sharp and definitive. After a 35-year journey, Voyager 1 had crossed the heliopause. On the far side, the sun's whisper faded, and the galaxy's background came up like tide. Years later, Voyager 2 felt the same switch. Proof that the border is real and that it breathes. How do you measure something that is nearly a perfect vacuum? How do you weigh a ghost? Instead, scientists had to rely on a more subtle and elegant method. They had to listen. They had to listen to the faint whispers of the void itself, using the plasma wave subsystem. This electrically charged gas can vibrate, much like the strings of a guitar. When a shock from the sun finally reaches interstellar space, it plucks the electrons like a tuning fork. Higher pitch means thicker plasma. No scoops, no jars, just listening in the dark and doing the math. Those tones arrive when shocks from the inner system finally reach the edge. Each tone is a data point, electron density at a specific time and place. Point by point, the dots become a profile of the local interstellar medium. Denser pockets. Thinner lanes. A structure you cannot see, but you can hear. Hearing beats seeing out here. Light is scarce, but the plasma still sings. And from that song, we learn how hard the galaxy presses on our bubble, how fast disturbances travel, and how the edge responds when the sun sends a distant storm. For decades, astronomers had tried to estimate the density of the interstellar medium using indirect methods. When the first data from Voyager's plasma wave measurements arrived, it delivered a genuine shock. The measurements from Voyager revealed a density of around 0.12 electrons per cubic centimeter. This was more than twice as high as most predictions. That one number redrew our local map. Not brick wall thick, still far emptier than any lab vacuum, but thick enough to shape our bubble, filter radiation, and change how a future probe will fly. The surprises did not end with just a higher average density. The density of the interstellar medium was not uniform. It was not a smooth, calm sea. Instead, it was filled with ripples, waves, and strange, large-scale structures. These waves could be the remnants of ancient supernova explosions, their ripples still traveling through the galaxy. Some waves come from us, storms on the sun that take months to arrive and then ring the edge like thunder. The border isn't quiet. It hums very slowly, and Voyager can hear it. One of the most significant discoveries Voyager made was how the interstellar magnetic field behaves right at the boundary of our heliosphere. The galactic magnetic field lines are forced to bend and pile up. They drape around our heliosphere, like fabric stretched over a ball. This phenomenon, known as magnetic draping, creates a sort of magnetic wall at the very edge of our solar system. Across that wall, particles don't move freely, they follow rails. A twist in the field can steer them in, hold them back, or send them sideways. Direction matters as much as strength. A small tilt can open a door for particles or shut it. Where field lines graze the boundary, energy can tangle and snap, then reconnect. That reshapes the traffic at the edge, what gets in, what is turned back, and what skims the surface. The magnetic wall isn't solid. It flexes with the solar cycle and the local flow, tightening and relaxing like a tide. For cosmic rays, these rails decide the route. For spacecraft, they set the rules, how antennas hold lock, how electronics age, how a probe should brace for the hail. The edge is a negotiator, not a brick. Beyond the sun's protective sphere of influence, space is not a quiet place. It's actually alive with a form of high-energy radiation known as galactic cosmic rays. They're like shrapnel from some of the most violent events in the universe, exploding stars or supernovae, powerful jets from supermassive black holes, and other more exotic cosmic accelerators. Inside the heliosphere, the solar wind takes the edge off that storm. Outside, there's no shelter, only the raw galactic hail. Electronics must be tough. For future crews, shielding isn't optional, it's survival. The moment of truth arrived for Voyager 1 in August of 2012. The number of high-energy galactic cosmic rays shot up dramatically, while solar particles plummeted to virtually zero. This was the smoking gun. The transition was remarkably sharp. Yet not the same everywhere. The edge shifts with the sun's cycle and the push of the local flow. It swells. It shrinks. Our two Voyagers met it from different angles and told the same story. It was like walking out of a quiet room and into a roaring storm. The discoveries made by Voyager about the cosmic winds and magnetic fields at our solar system's edge have profound, practical consequences for the future of space exploration. For any future probe designed to travel to another star, navigating this environment will be one of the primary challenges. Future interstellar probes will need to be built with radiation-hardened electronics. They'll need patience, too. Power is scarce. Data trickles home in whispers. Antennas must point true for years, clocks must keep faith, and engineers must design for the long quiet. Launch once, last forever. The discoveries made by the Voyager spacecraft at the edge of our solar system are more than just a local story. Our heliosphere is not just our home, it's a laboratory. Think of the galaxy as a giant, bustling city. Stars are the houses, and the interstellar medium is the atmosphere, the weather, and the public space that connects them all. These borders decide how much radiation reaches planets, how fast atmospheres wear away, and which chemistries can take root on cold worlds. To talk about habitability, we have to talk about space weather and the shields that shape it. The journey of the Voyager spacecraft has effectively given birth to a whole new field of study, the comparative science of astrospheres. This has opened up a cosmic zoo of astrospheres. We now know that they come in all shapes and sizes, depending on the type of star and the environment it inhabits. The incredible success of the Voyager mission has raised a host of new, more tantalizing questions. The next logical step is to design and build a spacecraft specifically for this purpose. One concept involves performing a powered slingshot maneuver around our sun, dipping in close to get a massive gravitational boost, and then firing a powerful rocket engine. Another idea is to sail, catching sunlight or a beam of lasers with a film thinner than a leaf. However we go, the payload must be wise more than bulky. Lean instruments, stingy with power, ruthless about mass. The plan is simple. Go fast. Measure everything. Measure the plasma, density, temperature, and how it changes with time. Trace the magnetic field, direction, strength, and the way it twists at the boundary. Count cosmic rays by energy to learn who gets in and who's turned aside. Listen for waves to map structure and sniff for dust and neutral atoms to see the flow itself. To get there fast, dive close to the sun for a powered slingshot, or unfurl a sail and ride light. To last, sip power, think for yourself, and phone home with narrow, perfect beams. A clock that keeps faith for decades. A brain that can make small decisions without waiting for Earth. One crossing won't be enough. We'll watch the line live. While the Voyager probes have revolutionized our understanding of the solar system's boundary, their journey has illuminated just as many new mysteries as it has solved. Perhaps the most fundamental question is about the true shape of our heliosphere. We have never seen our home from the outside, and its global structure remains one of the greatest unsolved puzzles. Is our bubble blunt-nosed or split-tailed? Smooth or frayed? Does it shed magnetic knots like storms? We have local readings and smart models, but not yet a portrait from the outside looking in. The journey of the Voyager spacecraft beyond the edge of our solar system is more than a scientific endeavor. It is a deeply human story. It speaks to our innate and unyielding curiosity. Bolted to each craft is a golden record, pictures, sounds, a hello from home. Not because someone will hear it soon, but because we wanted to send a goodwill note into the dark. Science answers questions. Exploration asks them out loud. Voyager has fundamentally changed our perspective on our place in the cosmos. We have journeyed together to the farthest reaches of human exploration. Here, at the boundary where the sun's influence fades into the galactic twilight, we have found a frontier that is not empty or silent. For millennia, our view of the universe was confined to what we could see from the inside looking out. We were island dwellers, our knowledge limited by the mists that shrouded the horizon. The Voyager probes changed that forever. They became our ships, sailing out beyond the familiar waters and sending back the first reports from the open ocean. The reports still arrive, faint, late, but clear enough to redraw the edge of home. Each downlink is a tide mark. Each one says the map is bigger than the story we told ourselves. In 1990, Voyager 1 captured an image of Earth as a pale blue dot. Now, decades later, the Voyagers have given us a new perspective. Our entire solar system would appear as just another small point of light, a single bubble adrift in the immense textured sea of the interstellar medium. And that bubble will change. Stars wander. Clouds drift. One day our sun will sail into a different current, and the shape of home will be made over again. We live in a moving sea. The story of Voyager is not over. Even now, two tiny, aging spacecraft are pushing deeper into the interstellar void, flying through a territory that remains utterly unknown. The legacy of Voyager is the inspiration it provides for the next generation of scientists, engineers, and explorers. Ambitious concepts for a new interstellar probe are already taking shape. Some designs aim to reach the edge in a single career. Others imagine fleets of small scouts, each learning one piece of the puzzle. Voyager lit the path. We won't rush it. We won't stop either. The desire to know what lies beyond is as strong as ever. Exploration is a fundamental part of who we are. It is an expression of our deepest nature. The edge of the solar system is not an endpoint. It is a gateway, an invitation to a much larger universe that is waiting to be explored. The cosmos beckons. The stars are calling, and we will continue to answer.